Luigi Brugnatelli, an Italian chemist, invented electroplating in 1805. He used a battery called a voltaic pile, invented by Alessandro Volta 5 years earlier, to deposit gold. However, Brugnatelli's work was suppressed by the French Academy of Sciences and Napoleon Bonaparte, leading him to stop publishing his work. In 1893, scientists in Britain and Russia independently created processes of copper electroplating for printing press plates. In 1846, a Birmingham doctor called John Wright discovered that potassium cyanide could be used as a salt in gold and silver electroplating. However, George and Henry Elkington, Wright's associates, were the ones who got the patent for Wright's electroplating process. The Elkingtons founded the electroplating industry in Birmingham and had a monopoly on the industry for quite some time. In 1876, the Nordische Raffinerie in Hamburg was the first modern electroplating plant to start production. From there, electroplating spread all over the world, and its many uses were discovered as knowledge of electrochemistry grew.
Electroplating is important to society because it allows us to manipulate resources around us, suit them to our needs and preference, and essentially make our lives easier. Common applications of electroplating include tin plating for steel cans to ensure food safety, and gold or silver plating of jewelry to enhance appearance. It is important to our society because electroplating allows us to create more efficient and lasting materials. At times, there is no material that perfectly suits our needs or purpose, but using electroplating, we are able to create products that have the perfect properties to suit its purpose. Electroplating is used in many industrial processes to modify metal machine parts, change the aesthetic properties of metal objects, such as jewelry, to decorate objects, and to change the chemical properties of certain metallic objects, such as solderability, wearability, friction, paint adhesion, conductivity, and more.
A metal object, in this case a key, is placed into a salt solution called an electrolyte. Our salt solution was copper sulfate because we wanted copper to be plated on the key. A piece of the metal is also submerged into the solution, and the cathode, the negative end of the battery, is attached to it. The positive end of the battery is attached to the key. The cations, or positively charged ions, in the electrolyte solution are attracted to the key, which is negatively charged. These positively charged ions gain electrons from the key and become solid, therefore plating the key. The anions, or negatively charged ions, of the piece of copper are attracted to the cations in the solution. Thus, they replenish the copper in the solution. As this whole process occurs, the piece of copper slowly gets smaller while the key gets larger. This is demonstrated in our lab.
We clean the copper ribbon and key with steel wool and then vinegar to get rid of any impurities on the surface of our objects. This way, the reaction will not be impeded by surface impurities.
Here is a diagram of the setup of our voltmeter, battery, ammeter, and plating station. The voltmeter was set up in parallel because it measures the difference in electrical potential between two separate points of a circuit, and therefore needs to connect to two separate locations. Electrical potential is basically a measure of how easy it is for electrons to move from one point to another. On the other hand, an ammeter must be set up in circuit because it measures the amount of electrons that flow through a wire. Here is a picture of our actual setup at this point without an ammeter.
Here is a setup of our copper plating station. Notice that the key was carefully placed in the beaker so that it was partially submerged, allowing for easy before and after comparison. Also, care was taken to prevent the key and copper from touching. This would allow electrons to flow between the two objects, completing the circuit and preventing the copper ribbon and key from becoming properly charged. As the key was being plated, there was an obvious color change from a lighter gold color to a darker color. When we took this key out of the solution, we found that a pinkish-brown layer had formed on the key. This was a layer of copper that had plated on the key. Soon after the color change was observed, copper began attaching to the tip of the key. This was because the key was already plated, but copper ions in the solution were still attracted to the negative charge. We noticed that after about 8.5 minutes, a solid began forming beneath the piece of copper. We concluded that, since this occurred after the color change of the key, that the key was already covered with copper, so no more copper could attach to the key. Therefore, any further copper ions that had disattached from the key would have simply become a solid.
When we had performed the electroplating process before, we hadn't obtained an ammeter yet, so by the time we had an ammeter, the key was already plated. Therefore, we attached a coin to our glass rod and repeated the electroplating process, this time with an ammeter rather than a voltmeter.
The copper ribbon decreased in mass, while the key increased in mass. Electroplating is a redox reaction. Here are the half-reaction equations. When the copper plates the key, the reaction is reduction. Copper cations join with 2 electrons to form solid copper. When the copper ions replenish the solution, it is oxidation. Copper solid loses 2 electrons and becomes copper cations.
In our experiment, we found that the current of electricity was at 15.7 amps and the voltage was at 7.3 volts. The power, or rate of transfer of energy, used in our experiment can be obtained by multiplying the current by the voltage to yield the number of watts. In our case, 15.7 amps times 7.3 volts equals 110 watts. The common household light bulb only uses around 60 watts. As saving the environment is becoming more and more important, we should consider how electroplating affects the environment. Simply plating half a key used more energy than having a fluorescent light bulb on for the same amount of time. Large-scale plants use even more energy, and electroplating requires 4 to 5 times more energy than painting metals onto an object. For these reasons, electroplating is not very energy efficient. The acids used in electroplating can often result in lesions and burns when brought into contact with skin. The solution we used, copper sulfate, is relatively mild as it can only cause minor skin irritations, though it can cause poisoning if ingested. Large-scale electroplating plants release toxic air emissions and wastewater. They are hazardous to human health and to the environment if the waste is not properly managed. For these reasons, electroplating is not particularly environmentally friendly, though because of its many uses, it is still very popular. Proper waste management and a transition to other metal coating techniques needs to happen in the future to protect the environment.